Good afternoon. We're into, I think this is the last week of daylight savings time, isn't it? I think it's going to happen this Sunday, I think. At any rate, it's sunny outside, but it's cold outside. And I experienced that with my dogs when I went running around noontime. It was mostly running and not too much walking because they're lean and they wanted to move fast, and that's a sign of the temperature change when your dogs want to move really fast. So I've got new things I put up here. I created an issue in a sense by something I did last year. This simple SA new Python file doesn't really exist anymore. It was an implementation that I did last fall, a year ago, to fix a problem, and then it eventually got incorporated into the SIGSys module. So that problem is behind us, and I tried to clean it all up, but I didn't have all the remnants of it out of there last week. I don't know if anybody needs to draw block diagrams, but I thought maybe you might need them. Why did I put draw IO up here? Oh, I guess it was because I thought you might want to use it for sketching in the homework. I drew my plots for the homework problems that involved the frequency spectra using FrameMaker, which is the tool that I have used for a decade or more. It's an expensive Adobe product that I bought with my savings account here at UCCS. I call it a savings account. It was my slush fund that money goes into when I had a research contract. So I still use that tool, even though it's a 2019 version. It still works really well. I also put up the new assignment. So let's just start by taking a quick look at that. It's not going to be anything that's we're going to be on top of immediately, but oh, it's the wrong one. Did I not get the link set right? It's possible. Wait a minute, I know what's wrong. I think I know what's wrong. Yeah, there it is. I work with 4 different computers, so when I don't update my browser after I've done a web page edit, I don't necessarily see what's going on. But so this set number 5, I put this heads up on here just to remind you, even though we're not even into November, we will be soon, that this is going to transpire for the second exam. There will be one other assignment beyond this one that will be incorporated into that exam. It will be Chapter 5. But you can see this assignment kind of tapers off in the sampling theory chapter, getting into the random variables, random processes, and some quantization noise stuff is down here. Those are all the things we have to get into tonight. So we're going to be doing that. But before I do that, I'm going to talk a little bit more about the project, because I think everybody's focusing their attention on it right now. I know Miles and Lake are for sure. Are you guys going to work together as a team? You can. Did you know that?
Sure.
You're undergraduate students, and I have the provision in there. John could work with you too, but he can only have 2 to a team. But yet I sort of figured he probably wants to work alone. I'm only surmising that, but yeah. Are you okay with that? I mean, 3 would just be too much.
Yeah.
And if you're a graduate student, you have to work by yourself. That's the one differentiator I have in the class for the projects. So.
There used to be more people in the class?
Oh, yeah. This class usually had between 20 and 30 people in it.
Really?
And as recently as 2019, I guess, it was usually hung around in the low teens, like 12, 13, 14, that type of number.
A guy named Cooper Tetstrom?
Yep. Yeah.
That was a long time ago. 7, 8 years ago?
Probably. I remember the name. I don't remember.
The person?
I remember the person, but I don't remember. Was he in this class? Was he in Com 2 or Com 1 or?
I think he was in DSP.
Okay.
What about Ryan Beckner?
Yeah.
Yeah. Barry Jackson. Oh. Yeah. Oh, really? Mm-hmm. Yeah.
There's people that were in my classes all over town. There's, absolutely no doubt about that. But and they work the places I've worked. They're at ARCA and any other place I've worked pretty much. So we'll get into this, but now what I want to do is just back away from this and go back over to the project, which I'm going to be a little bit slower because my radio knob for my mouse got left on a different computer at home, so I have to use my finger and my stylus. So I fixed little minor typos a lot in here, but I'm not really advertising all of them, but I did get this updated. So for one thing, I had forgotten that about Time It, and Miles brought that up to me yesterday when I was going up to the YMCA. And Time It, I mentioned IPython Magic, and I probably didn't mention the whole history behind Jupyter and IPython, but since I grew up as it was being developed, I was learning Python at the time these technologies were getting developed. IPython is basically intimately connected with Jupyter. What it was is IPython was more of a terminal environment, which it still is, and there's two versions of it that I use, and I'll fire one up tonight. And then Jupyter grew up underneath IPython, but then as it got bigger and bigger and being a web-based interface, the two development teams broke apart into two different open source development teams. And then Jupyter became known as Jupyter. But I think within Jupyter you see remnants of IPython. I'm not sure if the name is really in there or not, but the IPy widgets are widgets that work in the GUI-based Jupyter, which we'll be using in the project, and that itself tells you that it's connected somehow or another to IPython. So IPython was actually developed by a graduate PhD student in some medical field up at UC Boulder. So it's got a connection to the University of Colorado from its very beginning. And the idea of so-called magics, which is something I still don't understand, magic commands or something with percent signs, was something that was introduced by IPython that would basically be outside of Python per se, but if your shell knew how to interpret them, then you could do magic with them, I guess. I don't know. It was just special features that only worked within IPython and then also work in Jupyter. And it used to be you could find them, a list of them, and I might still have a link to them somewhere. I know on the old website I did, of the various magic commands. I only use a few of them though. So let's go just take a look at VS Code. And I put a link back on the web page over here, way up at the top. This takes you to a video. It's on the Microsoft website. It's really good. I went through it. It's better than something I wanted to try to tackle making. If you want to learn how to use VS Code and install extensions and everything, just watch this video. It'll tell you sort of the basic story. And some of you had already used it, right, John? You have used VS Code. Anybody else tried it yet? You may decide you want to try it. I'm going to use it tonight. So I have it running in here right now, and basically I try not to notebook open in Jupyter Lab and in VS Code Jupyter at the same time, you can do it. It's a little bit scary though, because if you edit it in, say, VS Code, and then you go back over to Jupyter, it will say the source has changed. Do you want to update it? And it will try to update it to match what you just did in Jupyter in VS Code, and vice versa. And it always makes me a little bit nervous that I might lose something because I'm updating the same file in two different locations. So I generally don't run it in both sides. But when you first bring it up, it doesn't have anything over here. It says what project do you want to use to open up an IPYNB, and it will let you search. And for me, it found my DSP-COM 313 from Miniconda, and I selected that one, and then it starts doing its thing. This little circle here that says restart is very similar or identical to what you can do in Jupyter Lab. Remember, you can restart your kernel and kind of clear everything out. So that was done here. But in order to get this up, the video tutorial from Microsoft takes you through some steps, and I'm going to not do that, but I'm going to try to open up the terminal window a little bit bigger here. But what you're basically doing once you get VS Code installed from Microsoft, then you want to put in certain extensions, and the extensions that I have installed are, let's see, trying to see if I can get them to display. I'm kind of a basket case without my mouse though. Fundamentally, I installed, I don't know why I can't see them all. There's too many different things in here to try to do without your mouse to make it frustrating. Yeah, I don't know how to do that. I can't slide that down. But these are where the extensions are on the left-hand side. I can't get it to show the Jupyter one right now for whatever reason. But that video takes you through the process of installing an extension into VS Code. And you had to do it probably, right?
Probably a long time ago.
Yeah, okay. You said it right, because I haven't done it for a very long time either. But sometimes when you launch VS Code, there'll be a number in here that'll indicate that one of these extensions needs to be restarted. And you'll also frequently see a number down here saying it needs to update the version of VS Code. And those are both very easy things to do. I just can't get the slider to work here. Okay, now I finally got it moving. There's Jupyter. And when you install Jupyter, if I was to go into that particular extension, it'll tell you about it. And then it will tell you some of the other sub-packages that maybe should go with it. And it pretty much guides you along, so it's not particularly difficult like Jupyter Notebook renderers. I really don't know exactly what they all do, but they're different features and things. So I tend to just go with the flow. And there's a star rating system on it, so lots of people have downloaded it. 97 million people have it. But notice what the rating is on it. It's not very high. So it's like people put up with it, is sort of my take on it. But the company, ARCA, on the Space Radio project, almost every engineer that I did sessions with in Teams, I saw evidence of their desktop that they were using VS Code. They were writing probably VHDL in it. They were writing C and C++. Other engineers that I worked with in the systems team were using it for Jupyter, for Python. So it's probably more popular amongst programmers than using Jupyter Lab. So you have to just make your own decisions on what you think helps you the most. But I am going to show you some features of this that are kind of nice. Question?
Oh, I think you answered it, but so we don't have to use VS Code. We can use
No.
Jupyter Lab
Yeah, just keep, if you really like that, you might just see something that you want to try out. It'll force you into a timeout, though, to go install something, but VS Code is not a big, heavy lifting install. It's very lightweight. And if you decided you wanted to do some other things that I wrote up on how to use it to create documents from exports through Markdown, that's another place that I've used it myself. So let's go back into here, and I'm going to close that, but I'm going to open Project 1. I've got 2 different notebooks in that zip, and that's the folder that I'm into right now. I unzipped Project 1 Fall 2025. I have a notebook that's just, I call it the Project Sample, so I thought I'd look at that one first, or try something in it, let's put it that way. But before I do that, I'm in a terminal, so you can open up PowerShell terminals down here. You can open up probably a terminal that you can launch and manipulate your Conda with. For me, on this computer, it's just in PowerShell, so you can see that I'm already pointing to the right virtual environment. And you can see all your things in here. And then, different from the way Jupyter Lab works, the outline, which would be like a code outline in general for C or some other programming language, the outline picks up the Markdown, and the M with the down arrow is the icon for Markdown. Makes sense, right? And remember, Markdown is just a simplified HTML that was created for documentation purposes a long time ago. So this acts like a table of contents, and you can click on it and it goes to different parts of the notebook, just like the one in Jupyter Lab. I think the Jupyter Lab setup works better, but if you're a coder and you like VS Code, then you stay in VS Code for everything. That's kind of the attractiveness of this. So when I was saying yesterday to you, Miles, about what else how could we run time it? So once you're pointing into an environment where you can run IPython, and that gets installed when you install Jupyter Lab, I can just type IPython and it will launch. And now I'm sitting in an IPython environment. This is something that's new, and I tried it today and I wasn't happy with it at all. It says Control-click to get the VS Code native REPL. And REPL is a term that's used in Julia and in Python both. We talked about that one night, right? What does it stand for again? Read, execute, print, loop. It goes way back in history for coding, where you want to develop and you want to be able to run code where you have this basic capability of read or write your code, execute it, have a print statement that'll print output, and then you can loop back on it again. So programming languages refer to that as a REPL, R-E-P-E-L. So at any rate, we're in here, and so I can use a magic. I just type %, and immediately it says, oh, you must want to do PyLab. And PyLab is now deprecated, but I still use it because it's been listed as deprecated, which means it's going to go away for a very long time. And it tells me how I can get around it, and I've been getting around it in the notebooks by doing things like this for you guys this semester. But what PyLab does is it imports all of NumPy and it imports matplotlib, so you can use it immediately. So it's kind of convenient here, and then I can just say I want to import, and you can see my last import was to import DSP Combat SIGSYS, so that's in there now. And then if I wanted to run Oops, I forgot the E. Yeah. Okay, I guess the last time I did this, I was timing it in FFT, so maybe I should just do that for a second, so you can see how that works. Create an index array of 1024 points, and then I'll just create a signal called X1. And here I've already got it defined from the last time I used it. It's pulling it back. So it's just going to create, oops, X18. FS wasn't defined, so I'll just backspace over that and put in a number for FS. So that's 18,000. Let's, from sampling theory standpoint, let's just make that be 100,000. And then I could go to my time it. Oops, what did I do wrong? I thought I defined it as X1, but it was X18, wasn't it? I'm getting all these different things defined in here because they're in the memory. So we just ran an FFT on a power of 2 FFT 1024. Later in the semester we'll be looking at this. That's where this example exists from. And I declared it to be 1024 points because that's what I started with, but the way the FFT function works in Python, if I say as my second argument I want it to be only a 1023 point transform, it's going to clip a point off the end. If I put in 1025, it would pad it with a 0 at the end. So I'll just run 1023, and we're going to see that it's not nearly as efficient to do a 1023 point FFT as it is a power of 2. So this is a good example of where time it is used. It's still pretty fast, though. 34.7 versus 47.8. But it is slower. That's notable there. And it runs, it says it ran 7 runs of 10,000 loops each, so it's just doing a lot to get good statistical variation. So it's a benchmarking means for an algorithm. But I don't want you to do it in IPython. I want you to just do it in JupyterLab or in Jupyter and VS Code because it's where you can document it in your notebook and everything. But for you, Miles, since you brought it up yesterday, I thought I'd prove it to you that, yeah, you can do it in here. And if I wanted to plot, suppose I wanted to plot that FFT. I can just plot it right here. I can go in and I can say absolute value of the complex output of that, which is X1. And then you see this little icon down here. That's the logo for Matplotlib. It's just a floating window. This is kind of like MATLAB, right? MATLAB would have a floating plot window, and this was the way this was originally created a long time ago by the creator of Matplotlib, who I think created it for Python because he wanted to have a graphics library similar to MATLAB's within Python. And the first few years that I went to the Scientific Python conference, he was present, but I didn't really know him as a celebrity. He's a not too old of an engineer, but he got some form of cancer and passed away. So he's in memory now of a lot of people. They talk about him as being the father of, Matplotlib. He doesn't maintain it anymore, obviously, but a team came in to maintain that project. So Sometimes I like the standalone plot window because when you're looking at a standalone plot window, and you can emulate this in the notebook, you can move cursors around in here, and you can zoom, and you can do different things that you don't necessarily do in the window of Jupyter. But there is other means of getting some of this capability right in Jupyter, but this is still, in my mind, the best way of getting that, marking points and things like that. So if I don't want to see that anymore, I can just Control D and say yes, get me out of it. And I can do Control L to clear it, but Control the back tick closes that window down, and then I can bring it back again if I want to. So usually when I'm using Jupyter within VS Code, I just get rid of the terminal window altogether and just look at this. So I'm going to run this kickoff cell. And you can see a blue bar running across the top, and you can see it took 5.3 seconds to load up all these lines. Oops. And most people like using the black background, or at least I definitely do, and I can't separate the two cursors, or the two sliders there, because they're right next to each other. And if you want to change colors within VS Code, you can go to Themes, and once you're in Themes, you can say Color Themes, and the default is what they call Dark Modern. There's very many variations on dark, though. Some of you play video games, and that's part of video games, isn't it, choosing backgrounds and things? So Dark Modern is the default, but the complement to that is Light Modern. So then we have, that. So maybe you like that better. To me, early in the morning, when I do that and I'm working, it's like my eyes start bugging out because it's kind of bright for me. So I tend to stay with the dark myself. And you can choose dark for VS or Jupyter Lab as well. Okay, so what's something that is very handy? This is the workup for problem 1, but let's go down to problem 2, where we're going to do this plot. So this just does a spectral plot with before any downsampling. It's this block diagram right here, but this is before you do the downsampling on it. So let's just run that cell, Shift Enter. Jupyter Lab tends to run faster than VS Code in terms of Shift Enter, but is always a trade-off. But now what I like Jupyter Lab for, though, you're hearing a lot of my things I don't care for. Suppose I wanted to set a breakpoint. You can just hover over here and you can set a breakpoint by clicking on it. And then if I want to do a debug, I can just say I want to debug that cell. And it will launch up the debugger. And I don't know how familiar you are using debuggers like with different coding environments, but up at the top there's the toolbar that controls the debugger, and it's set, we're stopped at the line that I put the debug breakpoint at. And then I can go down here. I'm now in the debug console, and because I'm in the debug console, I can look at things down in here as well as hovering. So right now, if I hover over N, since I've already ran through it, it's not quite showing up here like I was hoping it would. It's there, though. You can see at the top, we're hovering over N, and it's an array that goes from 0 up to 10,000. So we're seeing it right there. And then if I want to go do the next line, I would just go up here, and I get my choices of step over or step into. Step into, I wouldn't want to step into the cosine function, but if I was calling another function, I might want to step into something, but I'll just step over it. So now I have x, and you can see it's displayed off over here. And if you do this right, you can get a big panel to display. I'm not confident right now with this, the way things are without my mouse, but you can usually scroll all the way through, but you can also go down in here and you can just simply type x. You can type a value and it's guessing for me what it thinks I want to see. I could go from 10 to 20. So you can interactively step through your code and just explore what's going on. Now maybe you're so good that you never need to think like that. I mean, what do most of you do, or what have you done in the past? Print, probably, right? That's what the REPL idea comes from. You put a print statement in somewhere and see, what am I getting here? Why is the answer not right? So, but this allows you to do this in a more careful way and take your time about it. And then, of course, you can just zip off the end, and it will, finish the cell off for you. So that's what I wanted to show you in general on this part, but I do want to go through and demo from the other notebook I have in here, the Pi Audio Helper related stuff. So it's something just to think about when you're debugging. And you're on the debug menu when you do that, and you can see all the breakpoints that are set in various projects. If you don't clear them off, you can move around quite a bit. And I didn't point out that if you use a Git repository, that you have your version control ability here. If you're pushing something into a repository, say GitHub, then you can manage Git from here. Does anybody use Git in their capstone design? Teams sometimes do that because they have a common repository. In the work that I do at the companies, for the last more than 10 years, I've had to use Git. It's just part of the way you have to work at a company. So let's go over to the other notebook. I will just sort of minimize that off to the side. So I had some graphics in this one, which we had this set for white background. This would look like it does in Jupyter Lab, but I'm just going to run it from in here. I'm going to restart this because I ran it early this morning to verify that it works. I want to get the terminal to go away. So now I'll run this cell, which brings everything in. And then I drop down into here. We did this before many weeks ago, but just confirm everything's still the same. It's not the same because I'm connected to this interface, so I see things like Crestron 420 for audio, display audio, and I think I used that, didn't I? I don't remember. But right now I have been using 1 and 3 and all this stuff. Realtek in is on 1 and Realtek out is, well, I'm gonna output to Crestron 420, so that way it'll play through the speakers here. So I'm gonna use 1 and 4. Looks like it should work. Does anybody have any questions on this? When you start playing with this, you might want to ask me a question, but you can fumble around with it too. And this is a good example where things sometimes get hosed up where you have to restart your notebook. It's like it just sort of gets confused and it doesn't know what to do with the Pi Audio interface. And I don't know what to do with the fact that that is so close to the other one. So I played this earlier this morning, just the audio test. I'd recommend doing that, but I'm going to drop down here to one that I have a pre-built solution. This is the notebook that you write your solution in, so the code is not answered in here. There's just the setup stuff is in here. But there is one that, but since we were talking about spectrum, let's just stop there for a second, because this is pretty much identical to what you saw in 2610 when you collect some outputs from a buffer and then you want to get a spectrum, which is shown down here. You put the buffer into here, the number of points in the FFT, and that's going to be the vertical resolution for the frequency. And then the sampling rate is the last variable, I think. I think that's right. Yeah, it's 10,000 hertz, so there's 256 points spread in here, or maybe it's just 128, but at any rate, that's 0 to fs over 2, and then time is spread along here. And this is just a frequency step change, is all that example is doing. So what I want to do here is go on to this other example, though, which is if I can get it to work. Problem 5b is I've got a pre-built example in here, which is like a model for what you have to do. You're going to build up a variable cutoff frequency low-pass filter using FIR window, and you're going to have as the input a male speech test vector, and you're going to add noise to it. And then you're going to see what is the best cutoff frequency for intelligibility. This is a very subjective thing, but I just want you to do something, so you just have to play with it and listen. Like, if it's really noisy, how much filtering? It'd be like listening to a staticky baseball game on your AM radio and maybe taking the treble control and turning it all the way down to cut off the high frequencies. Maybe you've never done that before, but scratchy noise is kind of bothersome, so if you make it dull sounding by turning the high end down, it might be more intelligible. So you get to play with that. But in here, my pre-made example is to use a bandpass filter instead of a low-pass filter. So here I wrote a function to just define the bandpass filter coefficients from the math up above. So I'm running that. And then I'm going to introduce a bunch of sliders into here, very similar to what you have to do, but there's just more sliders in here than I think what you have to do in the problem. There's a slider. I get hit by that every time. I'm going to minimize that because it's getting in my way constantly. You can see there's a slider for center frequency, the bandwidth, signal to noise ratio, and then the gain. And then I'm going to get a pole zero plot of that filter. We'll have a better understanding of this once we were in chapter 5, but I'll just generate the pole zero plot. And there's another piece of code slipped inside of here, which is not so obvious at first, but we saw this when we were talking about continuity and initial conditions. That ZI bandpass filter is calling .lfiltIC, initial condition. The filter is designed in the line just above that, and then I create an initial condition vector based on the size of that filter. So you'll do something very similar for your filter, which is 32 taps or whatever length I wanted you to make it. And then I just plot in the poles and zeros, and we'll understand better that where there's a pole close to the unit circle, there's going to be a peak in the response, and then the frequency response will be zero gain, both at this point, which is DC, and then this is the folding frequency over here. And then for plotting responses, I've got a function that's in the IIR filter design helper, so I just imported that. And then I can get that response right here. And I could change parameters in this, and those parameters are going to be changing in real time. So here's the callback function, and you'll have to pattern what you do after what you see here in the callback function. You can see how I'm bringing in globals, and I'll go through this again. I'm going to just keep moving. I'm bringing in globals to control the vector of B coefficients and A coefficients for the bandpass filter. Also bring in the initial condition, so it gets taken back out, and then it gets pushed back in again when the next sample vector comes along from the audio I/O. And then I have a means of adding in noise right here, controlling, let's see, the gain gets controlled somewhere in here. I guess up above? No. Get samples, frame count. It's in here somewhere. I'm not laying my eyes on it right now. Oh, right there. So I'm controlling the gain that I hear at the output right here. But here I'm also adding in noise based on the SNR dot value for the GUI slider control. So anytime you see the name of a slider up above, the dot value is getting you the value of that slider, and that's how you get your control value from your GUI interface into the code that's running in real time. And then the values just pass out the end of this callback, and you don't mess with them. But I'm now going to come in on 1, and what was it, 4? Does anybody remember? Was it 4 or 5? Yeah, okay. So I'm going to see what this does. Oh, I didn't execute the callback. Build it, I mean. Okay, so now I've got my GUI interface that came up. These were the 4 sliders that were defined. Those 2 buttons at the top are defined automatically by the Pi Audio helper. So I can start streaming, and then I can adjust the gain here. I can adjust how much noise I'm going to add. So I'm at a 40 dB signal to noise ratio right now. And then this one controls the center frequency, the bandpass filter, and that one controls the bandwidth of the filter. And so now we'll listen to it, I think.
Paint the sockets in the wall dull green. The child crawled into the dense grass. Bribes fail where honest men work. Trampled
Okay, and now I've added some noise. Now I can play with the center frequency.
A round hole. Footprints showed the
This is the bandwidth slider.
Event near the edge, walking
Very narrow. Maybe it doesn't sound very exciting to you, but it's interesting. It sounds kind of like you're changing tone controls on a stereo, right? Because you think of the last one there is controlling the width of the spectrum that passes through, and the second to the last one is controlling where it's centered. And nominally you'd think, and the noise is flat all the way across the spectrum. So you'd think putting the center frequency about the center of the harmonics for the male voice would be the smart thing to do.
Paint the sockets in the wall dull green. The child crawled into the dense grass. Bribes
But the
fail
problem
where
with the
honest men
bandpass
work.
filter is that the
Trample
fidelity
the
and the
spark,
crispness of
else
the
the
sound is in
flames
the
will
overtones,
spread.
the higher harmonics.
The hilt of the sword
Whereas
was
the
carved
fundamental
with
doesn't
fine
really, it
design.
has more of a muddier
A
sound when
round
you only hear
hole
the
was
fundamental.
drilled through the
You're
thin
going to be
board.
just changing the cutoff frequency though in a low pass
Footprints
filter, but
showed the path he took
you get
up
a chance
the
to see
beach.
what it's like.
She was waiting at
What do
my
you think?
front lawn. A vent
It's-
near the edge brought
You know,
in
only
fresh
engineers
air.
can appreciate this stuff, but,
Prod the old mule with a crooked stick.
and because I'm
Paint the
looping,
sockets in the wall
it's just
dull
starting
green.
the test vector
The child
just keeps
crawled
playing
into
over
the
and over
dense
again.
grass. Bribes fail where honest men work. Trample the spark.
That's it. I'm going to go into the notes now.
So with the project, how do you want us to turn it in? And specifically for this problem, when we're adjusting the sliders to what we think is best, how should we convey that information to you?
Yeah, there is one problem with this, and that is that when you go to create a printout from this, the GUI sliders disappear. They won't show up in your printout no matter how you do it. The only way you can do it is you can do a screenshot of it and then overlay it in your notebook somehow or another, or integrate it somehow in the notebook. So what you can do, though, and what I would do and have done before, let me use this as an example. You can see here how I did a screenshot from the PDF handout for the project, and here I'm using a cell, and this could be a markdown. It is a markdown cell. You can see here it's markdown, and then I just use this command, image source. This is an HTML command, and then you can control the size of it there. So you can just do that screenshot and then place this markdown cell right underneath this, because when you transfer this to create a printout, this will be a bunch of error messages down here saying that it can't render the sliders. So just delete that in your file if you can edit it, or simply let it sit there and just put another cell in down here, like put a cell right below for markdown, and just insert that screenshot.
So you want us to send you the actual notebook?
Now I want you to print the notebook as a PDF. So here's how I'm going to have you do it. There's ways of printing in VS Code, but I have had better success with Jupyter. So I'm going to now kind of stop this part of the demo, and I'm going to go back over to Jupyter. So if I was sitting in here, like on chapter 4, let's say, or whatever we're doing, I would go down here and I would do save and export notebook as, and usually LaTeX is the best. You have to have the LaTeX typesetting system installed on your computer, and that's kind of like the dual to Typest. It's a much older system, and it's tried and true. It's free to download, but getting it working is tricky. You have to get some graphics installed. The other way I do it is I will export it to Markdown, and then I will get a Markdown file that has SVG graphics in there for every graphic that's in your notebook, and then you can take the Markdown file and convert it to PDF with an extension that you can plug into VS Code, and I have that on the website. There's a document on how to do that. But if you don't want to mess with that, the cleanest way to get it is to go HTML. I'm doing this live without knowing exactly how it's going to work. I know it works well on the Mac, but I'm pretty sure it works well here. It works good with Chrome, and Microsoft Edge uses the same underlying engine as Chrome does, I believe. Okay, so we have it. saved in downloads. My computer is just slow because I'm doing a video recording here though. So we will go create a new tab. Go look in downloads. And there it is. Is it going to open it up, or did it not understand me? There. Okay, so there it is. Equations are coming through, plots coming through. So generally what I would do then is I would go Control P and Microsoft Print to PDF. That's probably what I would do. And then, and I realize I'm making this so complicated, but it tends to be that way, unfortunately. If you have to hack it up or the page breaks aren't good, you can go ahead and, I gave you a link here, PDF file merging and PDF splitting. So you might follow this link here, which doesn't work anymore. So I'll have to figure out where that went to in terms of, splitting up a PDF, if that's what you need to do. You may not need to do that, though. It just kind of all depends on how you decide to go with it. If you were to export to Markdown, then you would have it in code, and then you could do exactly what I was saying about, well, never mind, let me back up. Before you export the whole notebook, what you would do is you would go ahead and put in a Markdown cell where you did the screenshot, and then it would get captured. That's what you want to do. Does that make sense? So you make sure you make that Markdown cell to put in the screenshot of when the GUI slider stuff was active. And then, of course, you write documentation in there, too. Like, these were the values that I chose that worked well. This project, I'm not asking you to turn in any files with audio in them, but I think if I follow through with my plans for the last project, we're going to be demodulating using this filter bank, FFT filter bank stuff. I will ask you to include WAV files that I can then listen to verify that you've got the capture of the right station and it makes sense. It's not just garbage, it's for real. If I can think of anything else that might be helpful, I mean, if you want to explore the Markdown technique, what you'd be looking at is this file here, where I talk about this will follow my link, because this document was created using a Markdown file. So here I install VS Code, I install extensions for VS Code, and then I get into this bit of editing right in VS Code, Markdown file that gets exported, and that's got all the code cells filled in, which transfer to PDFs directly. It's got the equations, and then it's got the plots are brought in like this. So what happens when you export as a Markdown file, you will have this Markdown file, and then you'll have a zip that will have all your graphics. And then when you bring it into VS Code and process it there to export as a PDF, it'll create that PDF that you see, in this folder here. And this explains how you do that in this document. It's a little bit more tedious, and it also tells you how you can insert a line of Markdown code to create a page break. But I think this also works in Jupyter Notebooks too. That's HTML code to force a page break. So you might experiment with that too. And if worse comes to worse, just screenshot and put screenshots in. And that's where types might come handy. Miles has got it totally perfected there, right?
Yeah.
He uses types not to write math, but he just uses it as a base to import screenshots. That was kind of like the minimalist idea that I had for having organization, and it makes it a lot easier for me to grade it because it is nicely organized. And you've got Lake, who's learning how to type in types. It's a learning process, right? I've critiqued a little bit of your coding
I
there.
have a lot of mistakes and times I'm just shotgunning it.
Yeah, well, but it's kind of working now, right? And you guys both are you're using a tablet. Tablet works great too. You use a tablet too, don't you?
No, I screenshot it and then I turn up the brightness on the picture.
How do you get your document though? That's just a direct screenshot?
So I screenshot, or I take pictures of all of my paper homework.
Right.
And then I just put it into a Word document.
And then
I
print it as PDF.
Pictures look and then print it as PDF.
Okay. Well, that works too. I mean, you could handle the Jupyter part that way too. You can selectively, and I did that in the very beginning too. Just try to get a good resolution. Don't have your notebook really tiny and then do a screenshot of that tiny section because then it gets really grainy when you blow it up. Try to capture it at the highest resolution, and then it'll work good for your approach, Miles. It works really well. I mean, I did that in the beginning myself, and then I started exploring other ways. I'm just giving you kind of a range of ideas. It's good to practice, though. Don't wait till the last minute to try to figure this out. Start, work out one problem and then just say, let me sit down and see if I can try it. Because I've got to do that myself. I mean, I've got problem 1 where I've got to do, or problem 3, I mean, that's a new problem for me. I haven't worked that one before. So I've got to meld that into my other solution. So I'm probably going to go with the markdown approach is what I'm thinking of doing. That's this problem right here. And then I'll just meld that in with my existing PDFs by splicing different PDF solutions together. That's how I'm going to do it. Because I am pretty particular about having a complete solution that just reads from top to bottom on this side of my tablet and then your paper's on the other side where I'm grading it. So I have to produce something in one continuous flow PDF, very much like you have to too. And what did I do in my work when I was finishing my documentation? I was doing something very similar. I was using types mostly, but I was using the HTML method a fair amount too, where I first export to HTML and then export by print to PDF, and that worked pretty good because I was making one contiguous flow document. I didn't have to deal with the GUI stuff, but I think my idea for the GUI I think will work okay if you just put that in before you export it, because it will render it as it will render it properly. Let's go back and look at that. Remember where was that? It's down here. I guess I don't have any pasted in graphics, but I'm pretty sure that they will render properly right here in the notebook. The only thing you're going to probably be frustrated with is page breaks, and you might possibly be able to tune that, but you'll have to go through this cycle of printing multiple times till you get the page breaks right, using that HTML command that I was showing over here, wherever that is. That div style page break after. This works well in the pure markdown version. I use that a lot. And then screenshots got inserted with this command, which you've already seen. So those are some techniques that you can try out. I've never been a fan of Microsoft Word. I used it a lot in the early days, but then I learned other things. So I will go to great extremes to avoid having to use Microsoft Word. And they haven't forced me to use it. Now, Confluence, that's something else. Have any of you heard of Confluence? Yeah, the companies I'm working at use it a lot, and they're trying to make me author stuff in Confluence, but I would rather produce like PDFs, and that's what I produced for my work, because I would have had to re-author to go into Confluence. But that's where Draw.io comes in too. I worked for one company where Draw.io was used a lot, and they even set up their own Draw.io server because it was all classified or secret stuff, and they had their own Draw.io server so that they knew it wasn't going to go outside the company in any way at all. Okay, I was reviewing this earlier, so I have to back up quite a bit.
I have a question about the exam two.
Okay.
It says it's supposed to be no later than Friday, November 21st, and then due by Tuesday. The Tuesday is November 25th. Is it due the day before the project?
That's nominally what I'd like to have. If it's at the same time, it doesn't really matter. The project is questionable right now, how that's going to fly myself. I say that because, let's get the month up here. I can stand over here then look at my calendar. We're going to come down through here, and I'll probably have the exam out earlier. It'll probably be out, 19, 20, 21, depending upon if I'm working again. Right now I haven't been working. I'm furloughed right now, so I'm having a lot more time to spend on this stuff. So I have it due here. The project was just sort of a last-ditch thing. What will happen if people are really struggling to get this done? I will let you bring that to me the week after Thanksgiving. Yeah, the project. The take-home definitely I want done by Tuesday. That's just like, you got to cut this off, you got to quit, you got to drop it if you want to carry on your life. It's never fun, right? That's one thing bad about take-homes. It's like, I don't want to give up on this thing, but you got to just, have a definite point. The project can slide over, and I was just thinking that would possibly be Wednesday because some of you might be going out of town. It's beginning to look like airlines are really going to be a difficulty right now until the government shutdown settles out. But actually, I've read that it's probably going to force the shutdown to settle. The government shutdown to settle faster, from what I've read. I don't know. What do you guys think?
No, I think it's just it's a political tool.
Yeah, everything's a political tool. Yeah. What did Israel and Gaza exchange fire recently? They just can't settle. That's all there is to it. Anything I read in that and Russia and Ukraine is all kind of botched up stuff in my mind. It's just carrying on. So,
Sorry.
That's okay.
So then after we do the project 1 and exam 2, then we have project 2 and then final all in December?
Yeah. Project 2 is pretty much, it is already up there. I might make a better file, SDR file, but yeah, that's pretty straightforward. There's lots of code developed. You're just pretty much just following rubrics and other things I've already set up, and you're just taking it through the motions and experimenting with the test vector. It's a big SDR test vector. That will not be that hard. You're learning more hands-on stuff, not in detailed code, but just at a big picture level, where you're just taking my lead, and I'm not asking you to just delve into it tremendously, whereas this project 1 has got a lot of detailed stuff that you have to go in and ferret out. And I've given you hints, though. There's nothing that you're totally left in the dark on. And I have more stuff I'd like to say, too, on project 1. I'm just not going to dump more right now, because I know that you have to fiddle around with stuff and get to the point where you're more receptive for needing help on something. Does that make sense? I know I'm that way. Don't give it to me all at once, because I won't be able to use it at all. I've got to get develop a need for it.
Do you expect that we'll get 2 more homework assignments for that meeting?
There is a set 6, it's a shorter one, I think that's due before, that'll be turned in just before the exam's given out.
Okay.
What'll actually happen, since you're asking the question, it's a good question. I always put out solutions, right? So you will have a homework set 6 that'll be due right on that Friday. I'll probably set 5 p.m. I'll probably already have the take-home in your hands, and you'll be starting to work some of the problems that relate to what you did in that problem 6. So you'd really like to be able to look at my solutions, but you'll have it for a day or so without it, and then as soon as I get all the papers from everybody on that Friday, then I'll post the solutions, and then you'll be moving along. So if we feel like, I say we as in the 4 of you feel like you might have problem set number 6 done sooner, that means I'll be able to post the solution sooner too. This is a university course, so things don't run with super wide, generous time allotments. They run more or less in a tight schedule. They have to. And of course, we are burning down towards as we burn down towards the end, things tend to get more crazy. They just always do. I try to avoid that, and I try to make it better. And I'm pretty confident, looking at the habits of all 4 of you, that you're going to this is going to work. Some of you are going to get done really early with the project. You'll come in to take the exam. You walk out of here, you'll be totally done. But yet I'll give you 24, 48 hours after you take that final. You'll take the final on a Tuesday. I'll probably say Thursday late is when your project is due. But some of you are going to turn it in before you even take the final. I just know it because I know how some of you are working. And then you'll come in and take that final on Tuesday, and then you're totally done. Does that sound like a possibility? Okay, we could take our break right now. Let's just take our break right now and then just come back in 10 minutes. 5:52, come back about 5 after 6, and then we'll start on this example here. Example that we were staring at but then moved off of it last week. This is a legacy example, and it's just shows you how multi-rate signal processing came along and saved the day in commercial compact disc. So remember, compact disc started in 1976, so it's been around a long time, but there were initially issues, and if you're looking at audio, which in the compact disc, the sampling rate is 44.1, and the folding frequency is at 22.05, so your audio content can go up to around 16 or so kilohertz. Our human hearing tends to drop off right there, so we really don't need to listen to overtones and instruments and things higher than that. So the folding frequency is at 22.05, but you do need to roll off the content of all of this so that none of it aliases back down into this band. I mean, I think all of you appreciate that. I'm thinking of that one problem where in part B, you downsampled by 8 versus downsampled by 4, right? Remember? So that it stretched it way out, and then that folded back around and created it was massive aliasing, right? So we need to cut this down. How do we do that? And we'll talk about that later in this chapter, where we end up with a really high order analog filter to do that. But by the same token, when you go to reconstruct it, and this problem was in the digital analog converter side. This was in the playback side, not the recording side. And I think in the compact disc world, the recording studio could have really expensive equipment, but it's the equipment that the homeowner has or the individual has. It had to be efficient, had to be low cost, and all that other good stuff. So here we have this spectrum coming back out, though, of the D to A converter. And Normally in the D to A converter, there's a zero-order hold. That's just the way the natural operation of the converter is. It does a conversion, and then it holds that value until the next conversion cycle. And that introduces a sine x over x kind of frequency response, and that's what you see in here. So it doesn't roll off really sharply. It also clips the edge right in here, but it puts out all this stuff. And although none of that is audible, it still would be driving the electronics and possibly could produce some distortions or overloading. It's best to just clean this up and get this squashed way down. And squashing down is just a crude sounding term, but it just says so many dB down. You never send it to 0, but you can push it down 10, 20, some additional numbers of dB. And to this day, you still have a sync correction filter, and you have a homework problem on that, on this set number 5 too, where you would possibly peak up to get rid of that little bit of roll-off there. But so here, the idea is they came along, and I say they, the electrical engineers in that day, shortly after 1976, said, we can make our D to A converter run 4 times faster. What does that buy for us? So they could output at the D to A at 176.4 kilosamples per second. And what that means is you can come in to the chain coming down through the DSP, and because now you're going to output at 176.4, the first image is going to be way up there. It's going to be a long ways away. You still need to roll this off, but your sync function is going to help in the zero-order hold. So you just have to build a high-order digital filter, and that was done in an ASIC that will push all the other stuff down in there. And that is sort of the story behind that. And why does it have an impact on me? Because I think in the very first compact disc player I bought from Radio Shack or something, it said it had a 4x oversampling D to A converter. So it was, you know, how in electronics they always put some sort of logo, have something in their advertising saying technology-wise why it's so much better. Did anybody understand what 4x oversampling meant? I don't think so. They just said, oh, it made it better, and people would buy it then, right? Is any of this sounding like, you know, it's not a sham, it's for real, but as an engineer, they probably said, if we can do this, we make things less expensive for us, right? They don't have to build an expensive analog filter. They could push the spectral image out there to 176.4. So when I got involved with different types of cellular telephony projects and things, I got exposed to this idea, and then I decided to write up an example here in the notes. And this was quite a few years ago, so I'm going to get to a part of this example where I'm talking about something that doesn't exist in Colorado Springs, but it was patterned after the marketplace here in Colorado Springs for cellular telephony. So we have, principally in the original cellular bands, we had an 850 megahertz centered band, and then we have a 1900 megahertz band. Now we have other bands further up that are available to us too, that have been made available through auctions. I don't know, do any of you understand? Have you ever heard of a spectrum auction before? Well, who controls the spectral bands in the United States? We have the Federal Communications Commission, right? And then there's organizations in each country, and then there's a international organization for spectrum management. Of course, during time of war, spectrum management is thrown out the window, and people jam, and people do whatever they want to do. But in terms of commercial systems, there's requirements and rules to play by. So when more frequency is going to be offered up, the FCC says maybe the government doesn't need this for military, this, that, and the other thing. We're going to carve out some more spectrum, and we're going to make it available to commercial entities. they always auction it off. They just don't give it away. They make people buy it. So different frequency bands were bought by all the service providers. Within the cellular band, there would have been, different cellular companies that would have vied to buy that spectrum at an auction. Like there were maybe 4 different bands available in Colorado Springs, in cellular, 6 in PCS or whatever, and then of course the markets are replicated all over the country, right? What goes on in Denver doesn't really alter what goes on here in the Springs, but it might be that AT&T went for the same auction in Colorado Springs as they did up in Denver, but it's all variable, and an auction it's very expensive. The spectrum is really expensive. You think, why don't cell towers build out faster? Well, the technology at the cell side is expensive, but then getting the frequency band was also very expensive. So all these investors put their money at risk, but they have a potential for great earnings too. So how do we build the handsets though, and how do we build the radios? So when we're going to do this in DSP, what we have to be able to do in a receiver is we have to be able to convert a complex signal down to baseband, and that complex signal has got a real part and an imaginary part, but in terms of digital communications, it's called an in-phase, which is the real part, and quadrature, which is the vertical. That would be the imaginary part. We have to get that off of a carrier, and the carrier is that 850 or 1900 megahertz. It might be a higher frequency, it depends on the application. The system I was working on for the Blue Moon project was at S-band, which is at 2.602, whatever it was. I had the frequency in my head from setting up equipment, but the exact number is not there anymore right now. But at any rate, that's the carrier frequency that carries it over from one antenna to the next. But then we come down to an intermediate frequency to get it shifted closer to complex baseband, where we're going to process it and then process it yet again. So the third option is called direct sampling, and this seems the most logical from a theoretical systems point of view. And we're systems people in here, so we just think mathematics, right? If we want to be simple and straightforward, we'd say mathematically we can just sample it directly. Well, we might not be thinking about what the electronics component makers are saying they can do for us. So direct sampling is still being dreamt about, and it's becoming more and more a reality every day, but it's not exactly the norm, I would say. So subsampling or IF sampling is still quite common in the industry. And I think in your lifetime you're going to see things continue to shift in that direction. For example, Analog Devices took a technique of the sigma delta converter ID, which we'll be talking about before we leave this chapter, which was for low pass A to Ds and D to As, the type that are used in CD players and so on. And then they modified that to a bandpass sigma delta. And I worked for a company here locally that was trying to develop their own variation on that, but I know Analog Devices definitely has it right now in parts. It's a bandpass sigma delta part. And it offers a direct sampling capability, is pretty much what it does. But this example is all about using the intermediate frequency option. So it's called IF sampling, and this is its block diagram. And if you don't like block diagrams, you shouldn't be a systems engineer either. I mean, because this is how we live. We live with a block diagram. It's giving us a top-level picture, architecture of our system, and we're always creating block diagrams. I found myself, when I was trying to explain something, I had to go to PowerPoint. Most recently, that's what I was using to draw my pictures rather than draw I/O, which I gave you the link to. But draw the picture, show the picture in your talk, and then show some results from Python about what the model is doing, but have the picture first. This is what I propose to do, so on and so forth. Does that make sense to you guys, you have your concept, and it's in your block diagram. So the radio signal comes in at 1900 megahertz. In this example, we convert it down to an intermediate frequency with a local oscillator, a stable crystal-controlled source, say in the handset. And then we have to pass it through an intermediate frequency. So we've got it taken off the microwave carrier. We're going to bring it down. In this case, this generation, because this is a fairly old IF frequency, but it's still possible to use this at 70 megahertz. And the type of narrow bandwidth filter that was effective for this application is known as a surface acoustic wave device, or SAW filter. And I don't know, is some of you have had are having Dr. Song for some class, but not, has she talked about SAW filters ever? Okay.
I think it's a microwave.
It is a microwave filter, but surface acoustic wave says you take a substrate, it's generally lithium niobate. Why do I know this? Because I had a class and we talked about that material. And you pattern it with some metallization and you launch a wave on it, but rather than it being like microstrip for a transmission line, it's actually an acoustic wave that travels across the surface of the substrate. And the patterning from one side to the other allows you to form filtering functions with the patterning. In my undergraduate degree, I had a microwave circuits class, and we learned about SAW filters way, way back then and how they were used. They're still used to this day. And it turns out, because of the overall business of making SAW filters, making them small to fit in handsets, making them efficient for low insertion loss and so on, it turns out 70 megahertz was a good frequency, but maybe 100 megahertz, 140 or whatever, some other frequencies are now used for SAW filters, but a lot of it had to do with, a bunch of parameters. And that's something that you see in every system design that I've been involved with. Why are you doing this? Why are you doing that? In your system architecture, it's because we're constrained by physical properties. You work for a device company. Your device company makes chips that only support certain clock frequencies, or, it goes on and on and on. So the system architects have to work around the constraints. But 70 megahertz was chosen. So once we have the 70 megahertz IF where our signal gets shifted to, then we have to decide how can we recover our channel off of that, our channel signal of interest. So we go with a wideband A to D that can sample directly at 70 megasamples per second or higher, and then we undersample the signal. And because of that narrow bandpass filter, where it's like that example I showed you in the animation that one day, it's just going to capture that narrow band, and as it undersamples it, it'll move it down in frequency, but it will be filtering out all the adjacent channels, like all the other cell phone channels. And it brings it down, and then finally it brings it down to 1/4 the final sampling rate, and that's why you see the 1/4 in here. Brings it down to that point, and then it takes it down once more by a factor of 2. And it picks the FS over 4 for a very specific reason, and I'm going to mention that in a second, but we're going to do 2 more processes, take it off the 1/4 sampling rate down to baseband itself right at 0 hertz, and then decimate it one more time. So the real picture in all of this is right here. There's the signal around the IF at 70 megahertz. The idea is we're going to take this and move it down around FS over 4. So that's the IF subsampling idea. Purposefully move it, and we're going to use what's called controlled aliasing. Remember, we talked about the bandpass sampling a little bit. So we jiggle it into place. I'm saying jiggle it because the IF minus M, namely the nth harmonic of FS, is going to be related to FS, or constrained to be FS over 4. And then we need to make sure fs/2, our folding frequency, is greater than the bandwidth of the signal. Remember, that's our sampling theorem idea right there. So this, I'm just looking at the pictures. You can read the words on your own. So this is what it amounts to. And I've already shown you this weeks ago, right? Remember when I did that demo with a slider and everything? So it drops it in down there at fs/4. In some instances, when this idea is applied, the signal might get flipped. In this case, it doesn't, but you can see here it's reversed. In some applications, flipping a signal over, it might have some symmetry in the modulation or asymmetry in the modulation that flipping it would be bad, so you would pick a different harmonic to make sure you don't flip it. That can happen if there's sidebands and other things that are encoded onto the modulation, like TV waveforms, for example, have traditionally been what's called vestigial sideband, where the signal has got a carrier, but most of the information is up at the higher end or below the carrier. And even though the newer TV signal is purely digital, it still uses this vestigial sideband idea. And vestigial sounds weird to you. It's a word in the dictionary, right? Vestige would mean there's a bigger picture, and a vestige would be something that's the remainder. It's like the big thing is here, but the vestige of it is the smaller thing. And in modulation theory, most modulation schemes end up with a two-sided spectrum centered on a carrier, and if you can eliminate one of those sidebands because you don't really need it, that saves a lot of bandwidth. It allows more signals to be packed together. But there's a lot of other techniques in digital comm that manage that too. At any rate, you come down and shift it down by that last 1/4, and the cool thing about that is that when it's up there at 1/4 and you do a complex frequency shift, you're multiplying by an e to the minus j. So that means the shaded one just moves to the left, and what's here, everything else moves to the left. It's not like one moves down, the other moves up. When you do a complex multiply, you get to shift it left or right. And that's beautiful, and that's what we wanted. And because of the way this works out in here, the 2 pi divided by 4 ends up being pi over 2. And then when the t gets in there with fs, we end up with the sine and the cosine becoming just pi n over 2, which means the multiplications don't really have to happen. They just become 0, 1, and minus 1. Does that strike you in any way? I mean, to me, it's like, wow, this is amazing. Somebody thought about this and said, if I don't have to really multiply, I can just do a sign change or multiply by 0, have 0 come out. I can get that translation to occur, and that's my estimation and how I've read about this in a couple of books and the original paper. This was a technique to make it very efficient, not to have a real multiply involved. You're going to see a lot of that in every place you go in engineering world. People have done something slick like that. What do you think? You'll ever come up with something like that? I mean, it happens all the time. You say, I could do it like this, I could do it like that, but if I do it like this, it makes it easier. And who doesn't want to make their life easier by designing in a particular way? I could think of an example, but it could be something as mundane as taking, well, for me, Tuesday is garbage day at my house, so I don't have an example in mind, but I know there's something about my habit of how I take the bags out of the kitchen and from this other part carry them down. There's something I do that I know I've learned by repetition. I want to do it in that order, in that way, shape, or form, and that's kind of, I think, the whole idea of innovation in engineering is you realize there's a dumb way and there's a smart way to do it, and you just figure that out by doing it multiple times. They're playing around with it, say in Python. So that translation is really nice, and then you can take it down because it's double wide at that point. The sampling rate's wider than what it needs to be up here, because when we slide it over, it's already less than pi over 2, not just less than pi. So we can decimate it one more time And now we've got the sampling rate small enough for making instructions per second be more reasonable. And the way I finish this example off, this was in the second generation of cellular, and it was a standard called IS-95. Now, I'll tell you, IS stands for interim standard, which is kind of dumb sounding, but that's just the way cell technologies work. Back in this day, Qualcomm had invented or created this standard, the code division multiple access scheme, which is not used in today's cellular, but remnants of CDMA are still in today's wireless standards. They're floating around. And in Colorado Springs, it was called the Block E band that Quest Networks bought. Does anybody remember Quest? The history behind Quest? Because you're not too young to not remember this. Remember driving up to Denver and seeing a high-rise building that had Quest written on it? You didn't live here? Okay. How about you guys who grew up here?
I don't remember.
Okay. They sold out to the current, Quest was who we paid our phone bills to. They were our wired line provider, and then they also had cellular business. So at the time, it was a Quest band, but it's been inherited by somebody in Colorado Springs. But that's the Block E band, and I suppose that I was going to pick up a IS-95 signal at 1887.5, has a bandwidth of 1.25 megahertz. It's got a chip rate of 1.2288 megachips per second, and it has some spread on that, so it spreads out to 1.25 megahertz. Chose 6 samples per chip, which meant FS is at 7.37, FS over 4 is 1.832, and then fiddling around with what M needs to be. M equals 9 worked well enough so that the IF frequency was shifted just slightly to fit still within the SAW design parameters down to 68. And the local oscillator has to be that. So this is kind of, the concept was early on. The final details of how to implement it are just right here. That's also a trademark of system level design. You have the concept, and then you give me the specific numbers, and I'll tell you this has to be that, that has to be that, and so on and so forth. Sound okay? It's just another, kind of motivation to say multi-rate is pretty valuable. Multi-rate has definitely been around for a long time. It's not going to disappear, as far as I can tell. So we talked about multi-rate a bunch, a couple other examples, and I have to keep track of the time here because there are no homework problems on this, but I want to still go through it. When we do upsampling and downsampling, we've seen at least in that one homework problem I'm thinking of that had the upsampler, the filter, and then the downsampler. That's the problem that had the A and B parts, remember? So when you want to do rate changing by rational number, that's the order. You upsample, filter, and downsample. And if you just have to downsample, let's say, or just have to upsample, and it's not a matter of a rational number, but it's just a single integer up or down, we have two identities that are very popular. There's a downsampling identity and an upsampling identity. And what they bring on the scene is this idea of polyphase filtering, or they lead to polyphase filtering. So the idea here is that when we first saw decimating, we saw it like this. And my pen just, yeah, there we go. We saw it like that. Remember, we had a filter, and ignore the Z to the M, but we had to low-pass filter to avoid aliasing and then downsample. But the problem with this is we're doing all the filtering right there at the higher rate. We're doing more multiplies than we feel like we should do, and then when we go to the decimator, what are we doing? Throwing away samples. Dumb, right? That's sort of a classical dumbness. Now in Python, you can prototype to your heart's content. It's not going to kill you to spend a bit more time, but in a real system, you'd want to do something with polyphase. So what the sampling, this identity says is we can decimate first and we can filter second. And there's some tricks and constraints on the design of the filter that make that all that possible. So I'm not going to go through the super details of the math. I'm just going to say that there is an identity that allows the downsampling to happen first, and it's based on winding the math inside. So I'm just going to use pictures. The same is true in upsampling. In upsampling, we were showing this where you would upsample and then you would interpolate afterwards. And again, we upsample and now the filter comes and we have the upsampled rate. We're doing a lot more work there because we're at a higher rate and we're going to do all that upsampling. But yet, what makes this dumb, obviously dumb, is that this pumps in a lot of zeros. So this filter is seeing a lot of zeros get stuffed into it, which means there's multiplies that don't really do anything if you multiply them by 0. So that identity up above says that no, we can filter first and then upsample and make it more intelligent. So how that works out is through the idea of the polyphase decompositions. This is what I showed you on that slide from that magazine article, remember? I think I still have it up here. If it will open up again. Yeah. In the end, this was the idea of polyphase interpolation and polyphase decimation. So the decomposition says we take the filter that we've been seeing in this identities, the upsampling identity and the downsampling identity, and we're going to create subfilters from it. So the idea of the subfilters, this is just a special case of m is equal to 2. So you take these filters and break them into 2 smaller filters. One that's got the even points and one that's got the odd. So you look at this and you say, I don't see any savings in there. Well, you get the savings because when you collapse this down, those 0 points are gone away. So these filters are half the length of the original filter, but we've got 2 of them. So that doesn't seem like that can really save you anything, but that's sort of the mysterious thing about this identity, the way this will work out. It will work out in the end. So and if we have to decimate by more, we would break it up into more than 2 filters, but here we're decimating by 2, so we have 2 subfilters. So we have the 2 shorter filters. This is kind of a block diagram, the initial block diagram, the concept block diagram for the polyphase decomposition. The problem with it is it's not physically realizable. This is like a stepping stone, and where this is impractical, it has a z rather than a z to the minus 1. So that's, rather than a delay, that's an advance. And what is an advance in a real-time system? It's non-causal, right? But somebody came up with this as a way of explaining how this works by just saying that this is how we could utilize the polyphase components. And again, I'm just looking at the picture. So what makes this bear out properly, though, is when we just look at how we could filter a signal with the polyphase filters, we could take signal x of n gets polyphase coefficients from E0 raised to the nth power, z to the m, so that's going to space the filters back out, the taps back out again, and that's where the z to the m business, which we saw in the identity, comes into the play. When you replace in a z transform, you replace z by z squared, that's going to be two delays away rather than one, and so on and so forth. But this will mathematically implement this, is all I'm saying. I'm not proving it, I'm just sort of waving my hand at it. But if we have this structure, then we can now formally go ahead and make this proof. So this is what we want to replace, and the idea is it comes along like this. It says we're going to take what we just had, which had a filter, which was a subfilter with a z to the m in it, followed by a downsampler, and we're going to take that identity that we looked at, and that identity was set up exactly like this. It had z to the m before the downsampler, and then we can turn it around and put the downsampler first, followed by the filter. You'd have to go back and look at that if you're not remembering it properly, but it was right up here. That was the occasion of how this identity was developed. It says if we have this type of situation, the identity can be shown, and I just am not wanting to go through the math right now to say that the upper is possible. I mean, I said that wrong. That the lower is possible. So we want to be able to have the filter, we want to have the filter come last. I have to keep my mind focused on what the problem is. So here we have all the decimating happening afterwards, whereas if we use that identity now, we can decimate first and then filter, and then this will allow us to decimate the high rate signal down initially, and then the multiplies and adds on these filters run at the lower rate, and that accomplishes the end game of the polyphase. And the savings are this amount. Direct implementation would require about n multiplies, and with a polyphase, n over m. So you can get a significant savings as m and n and m are, well, as m gets larger, I guess. And as the number of taps, m is the amount of decimation you're doing. And the same idea works in the opposite direction. I'm not really going to spend any time on that, but it will work out that you can filter before you upsample to do the polyphase upsampling, and then you get a similar amount of gain. And I guess since I've got this here, this in my mind is the easiest way to think about how the polyphase downsample and upsample works, because this is a mechanical kind of an idea that you've got a commutator that's going to go around and sample each of these outputs of this upsampler. So an input comes in here, it gets filtered by the subfilter, all these subfilters. So it will produce one sample output for each sample input of this shortened length filter, but then the commutator is running at the higher rate because that's going to produce the upsampled output, right? So one sample comes in here, we get L samples across here as this commutator sweeps around and puts those samples out in order, and do that again, and it just keeps happening like that. And these filters are more efficient because we're not working with any zero samples like we would in the ordinary upsample where we'd stuff in zeros. These are all live multiplies in the sense that there's numbers getting multiplied and added together. And likewise on the downsampler side, as the signal comes in and the commutator in order feeds samples to these various inputs, because now we're going to get a lower output, so it just sweeps across here and feeds all the inputs in to drive these subfilters, and then all of those are combined together to form the lower rate output. So the input's coming in faster, it gets distributed across all the filters, the subfilters, and then they get combined. If you're worried about making one, they're available. I mean, they're available in Fabric for FPGAs, they're available in libraries. So I did have a project problem. Problem number 3, again, at one time was building a polyphase in Python. I found it wasn't a very satisfying problem to have people work on, and I went after it because I thought I could show that it would be faster in Python, but Python's not super fast to begin with. Then I modified the problem, and the last time I used the problem, I had everybody learn enough about Julia to see the difference there. And in Julia, because it's compiled just in time, in Julia it makes a huge difference to go with a polyphase versus a non-polyphase. And Julia has polyphase filters in its catalog, in its DSP library. I don't think Python does. I'm not positive. It might have them in some NumPy, or not NumPy, but in the scipy.signal, there might be polyphase in there. But just the concept of it is important to be aware of. And if somebody was doing polyphase, and I know other people that I've worked with are doing it in C++, people at Arca, they use polyphase stuff. And I used it in an ASIC project at Atmel, which is whatchamacallit, microchip now. I use it in a project there, and I combined it with a synchronizer for a spread spectrum waveform. So I actually had a correlator, which is a filtering operation that I built in a polyphase structure. I would have liked to have written about it in a paper, but because it was done with a company confidentiality, it's just in my head, fading away slowly but surely. It was pretty cool, though. I liked it myself. It was just an idea that ended up going into an ASIC. And then the project was canceled, and it never went anywhere beyond that. But if you get involved with polyphase, you would get a chance to play with it. It's pretty much the way people do things today, if they're higher order things. Now, what did we do in the project I just came off of? I worked on the transmitter a little bit. They needed to do some filtering at the output to meet an emissions requirement. So we came up with a very simple moving average filter, a cascade of moving average filters that that had very low complexity, and that was able to shape the spectrum enough to meet the emissions requirement. So that was not a polyphase. That was just the FPGA people implemented directly, and I modeled it all in Python and verified that it met the spectral mass of the NTIA, which has got an office up in Boulder, National Telecommunications Institute. What does the A stand for? I don't remember. Hemispheric or something? I don't know. NTIA holds another set of requirements that radio people run into when they're building things. You have the FCC for emissions, and then spectral occupancy is an FCC concern as well, but NTIA is one I bumped into in the last 2 projects I've worked on. It's all revolved around space emissions coming onto the Earth and whether or not the emissions are too powerful to interfere with local terrestrial transmissions. And that's something that GPS also has to abide by we love GPS, right, because it can tell us where we're at. So when the GPS signal was arrived at, it had to meet a spectral emissions requirement, and it had to be. It factors into the accuracy of the geolocation, but it also has to be a low enough power density. Density watts per hertz is what it comes down to, and that keeps the NTIA happy if we do that. Again, all of this stuff is subject to playing by the rules, and I always say that because if there's a time of conflict or something, people are going to do whatever they want to do to accomplish what they want to accomplish. But it's pretty nice the way we can do that. We don't have things get interfered with. I don't know, does anybody have an issue with a microwave oven interfering with their Wi-Fi? We have a problem at my house. If the oven's on, our Wi-Fi can get seriously impaired. And I brought home a Field Fox spectrum analyzer from the comm lab and verified that it emits quite a bit right in the Wi-Fi band, and that was the creation of Wi-Fi. They knew when Wi-Fi was coming and emerging. Microwave ovens were much earlier. They had an unlicensed band right next to where Wi-Fi was trying to operate, and microwave ovens were there first, and Wi-Fi had to figure out how to work with them. Cooking food with microwaves and communicating with microwaves in that same band where 2.4 gigahertz have always been kind of a problem. Just like I worked on another project for satellite communications, the Air Force Satellite Control Network, AFSCN, I worked on that project, and we were looking at spectral emissions and other things we could do in the Air Force Satellite Control Network, because TV stations that do remote broadcasts, you've seen that on the news at night where they're remoting somewhere and they're going on an uplink to Cheyenne Mountain and then back to the studio or whatever, however they do it. That also was interfering because it's right adjacent to a military band, so they were getting interfered with by AFSCN. Tough stuff, radio interference, but it happens. Okay, what we're going to move into now, before we can get into applications of quantization, which you do see on the next homework, we're going to have a quick look at probability and random variables, and then immediately jump into random processes. So everybody had prob and stats for engineers, electrical engineers, right? You've had all the right stuff. And I think it's good to know if you're a signal processing person or a communications person, you use this stuff in a very positive way for looking at noise, which we just heard in that example earlier. That's what we're generally up against in a comm system, is noise, and in this signal processing in general. The other people that bounce into it a lot are control systems people too, but I think they have it in a different sense. So Dr. Platt and Dr. Trimboli have it in a different sense. They have randomness modeled, but in communications and signal processing, it's like in your face. It's just you want to operate right at the noise floor pretty much and a receiver, because you want to get as much bang for your buck out of it. You want to get as biggest range. And how many of you wear Bluetooth, anything to listen to music on? Where can you go in your house when you're on your Bluetooth with your device that you're listening to your music off of is here? You can be quite a ways away, right? That's what it's all about. And Bluetooth actually inherently interferes with itself and Wi-Fi. So it's got it hops to different frequencies, and it uses the probability associated with those hops and not colliding too often and coding to allow you to use Bluetooth. A lot of Bluetooth users, like I'm using Bluetooth right now, you might be using Bluetooth on something, on a mouse or whatever, and they manage, amazingly enough, not to really seemingly interfere with each other. Have you ever not noticed that? I would say probably not, because I rarely notice it, but yet I know it can happen because it's part of the design, and hopping around is part of what it does to mitigate that. So probability is founded in basic concepts like events and sample spaces. So the first thing here is sample space. Sample space is where the experiment actually takes place. The sample space for flipping a coin is just got head and tail. If it's rolling a die, it's got 6. If it's looking at noise, like Gaussian noise in the receiver front end of a radio or something, it's something that it's due to random electron motion. So it's actually got this Gaussian distribution, and what do we know about a Gaussian type statistic is it can range theoretically from minus to plus infinity. It doesn't really hit that, no, but modeling wise it's still based on something like that. And an event is a collection of elementary outcomes in the sample space that correspond to something of interest, like an even in the roll of a die, let's say, or a number that lies on some interval in the case of a continuous type event. I'm thinking of board games that have spinners on them, which probably none of you play very often anymore. I know I don't. My family really likes certain types of games that don't use any of those gadgets anymore. We do different strategy type games, but when I was growing up, we had a game where you'd have to spin something and then where it stops. So dice and cards show up, of course, but so once we have the sample space and once we have the events space, we have certain events, which is like the event that something occurred within the sample space, and we have the impossible event, nothing occurred, which never happens. Then we can start assigning probabilities to those events, and then we have the axioms of probability that says probability of an event is greater than or equal to 0, the probability of a certain event is 1, and then the special formula that you remember, probability of the intersection of two events is not equal to 0, then it's equivalent to the probability of the union is equal to the well, if they're disjoint, I mean, then the probability of the union is the sum of the probabilities, and then we extend that off to total probability with an countably infinite number of events. And then beyond the unioning, there's the intersecting of two events, A and B. We have a theorem for that pops up, I think, somewhere down the road here. I guess conditional probability comes up first. I guess it doesn't come up in here. Turns out we don't need everything. We don't need a whole lot of probability theory to actually get going in random processes, but the underpinning is probability, and then random variables is the next level of that. So I was thinking of a theorem that would be a homework problem in probability theory, but it's not I don't have an example of that in here, and it's not relevant right now, actually. But joint probability would be the intersection, and then conditional probability are concepts that are important in some of the modeling that we're going to do. If you have two events and you think about what's the probability of one event occurring given that another event has already occurred, so probability of A given B, that's the probability of the intersection normalized by the probability of that conditioning event B. And then you can turn that around and get B conditioned on A, and then you can bring those two together and form Bayes' theorem or Bayes' rule, which says you can go from one conditioning A on B to conditioning on B on A, and the two so-called marginal probabilities. Remember that idea. P of A and P of B are the marginal probabilities. And then that turns into the total probability idea. where you can get a probability of interest by breaking it up into parts, I guess. If the sample space is in red and then the conditioning events are P of B would be the probability, the sum of the probability of B given AI, and that sub-event, PAI, and then you can divide and conquer. And this is maybe, again, an underlying concept in what we're going to talk about. It's more important in the class you've already taken, but you remember that this idea certainly existed. What is very important and what we assume here is we try to keep things from getting out of control and too complex, so we're going to make assumptions on independence. We're going to assume processes or noise and signal are independent of each other. So if we have the probability of intersection of two events A and B, it becomes the product of their probabilities. And if we're talking about conditional probabilities, the conditioning doesn't matter in the case of independent events. So, and I know it seems like I practically said nothing because there's a whole lot of probability in other needs and other activities, like in comm systems too, and those notes are on the my website right now. Ironically enough, somebody wrote to Dr. Trimboli yesterday saying he wanted to come to graduate school here and take classes in statistical signal processing, which I used to teach, and learn about random processes. And I was sending him some information. I don't know who will teach the class though, but I definitely have the videos and the lecture notes that go with it. And right now, there's a whole chapter on random processes in the COM2 lecture notes. And then here we have a more abbreviated set of definitions just for discrete time random processes, and that's what we do in this class. But when I first started teaching here, I taught a whole semester's class on probability, random variables, and random processes. I did that over and over and over again. At one time, when I first started teaching, we had a core of master's level courses, and students had to take, I think, 3 of the 4 core classes. So I had a lot of people in that class regularly, and it guaranteed I had enrollment. And then we had to quit teaching it. I remember the semester, it was always taught in the fall. I usually taught random processes and this class together, and the enrollment dropped below a certain number, and that was it. I mean, the class was canceled, and it has never been taught since then. Then 5615, which was random statistical signal processing, came along as a replacement that I developed to try to have a blend of different topics in this area. And that's what this student that wrote is really interested in. It is, in my estimation, a pretty important class, but it's still being overruled by machine learning and probably AI to some extent. And the take on it, my take on it, is that statistical signal processing is actually very, very important, but it's not easy, and it's a more traditional subject of just working with random variables and random processes rather than the rubrics and rules that you can play with machine learning, let's say. So machine learning can work over the domain of statistical signal processing, but it doesn't necessarily require as much in-depth math because you're using just standard rubrics and things to take a set of test vectors or a set of collected data set and then processing it on certain algorithms. I don't know if anybody's ever talked to somebody in data science, because we do have a program here at UCCS. Does anybody know of anybody that's in the data science courses?
Data analytics?
Yeah.
I had a friend who did that.
You're,
He's DZ,
pardon me?
data analytics system engineer.
Yeah.
Yeah, I think it's still, Michael.
Yeah, that's a course that he teaches, yeah, but that's different than statistical signal processing, which is more math focused. Data analytics is just applying certain rubrics to data sets and things. And I guess the scary thing about it is that it comes under the heading that was really popular quite a number of years ago called big data. And we are in big data right now, because what happens as soon as you go to the doctor or do anything, go to a restaurant, they're wanting you to fill out a survey and give them some data for their big data engine so they can just munch on it and form some analytical, decision theory on what we're going to do or not going to do. Have you ever felt that way? I personally don't like filling out those surveys. They take time, and I'm helping you, with your job or something like that, and you're not giving me anything extra. You asked me to pay a tip before I even got my food at a stand-up restaurant. I'm also aggravated by that, because I think tipping should be for when you have a sit-down and a server giving you personal attention. How do you earn a tip? By just serving the food right from the counter. There's something. When I was been in Europe last year, Europe doesn't work that way at all. You don't tip at all. You just buy your food and that's that. So things have gone a little bit strange in my opinion when you're expected to pay a tip, and it's like, wait a minute, I don't even know if I'm going to like what you're going to serve me. But you guys are younger. Maybe you want to help everybody out because you just want to do that. No. But you haven't been having to pay a tip for as many years as, say, I have, and I find it just kind of foreign that all of a sudden it's in your face every time you turn around. I digress, but probability and stats and big data, they still want your survey when you get done. They're still going to ask you to fill out a survey in an email.
You should get a tip jar and just have it sitting on the table during your lectures.
Oh, make some extra money. I'm bothered by that, but that's easy. You just don't do it if you don't feel like it's the right thing. But the surveys, you have to delete the text messages and the emails that you get all the time. For my hand surgery, I got, I'll say, a handful of things evaluated. And I guess, according to my sister, who's a medical doctor, saying that medical workers, their job is weighed upon how those evaluations come in. So actually, it's important to them. I just wish there was a better way of getting that information into the powers that be with their data analytics stuff. So stepping up from probability, we now go into the world of a random variable. And this, I think, in my estimation, is the most fun part of probability, random variables, and random processes. And as an electrical engineer, this is where you really see things happening. I don't know if when you took the stats class, you had an opinion, like you had probability, pure probability problems, then you go into random variables, and then maybe some applications of random variables in statistics or fitting data or something like that. Do you have any appreciation for or any opinions on which you like the most? Probability, say, versus random variables, which was?
Probably statistics.
Okay, towards the end of the class. How about the front part with probability problems? You like those? I tend to find that those problems are very aggravating because they're like story problems from way back in high school or something, where you had to read, a story problem, then you have to figure out what are you asking for. I don't understand.
But it actually has math.
It has math inside of it, but story problems are traditionally can be vague or list. You get led astray. I like random variables the best myself. They're just, you get to work with PDFs, and things tend to work out pretty nice. Not trivial, but still they work out pretty nice. So you take the outcomes of a random experiment, put them on a real line, and then you've got a random variable. So now you can start thinking of it in terms of intervals. You have a distribution function if it's the interval less than or equal to the random variable, the boldface character is less than or equal to some little x. And then you have characteristics like as little x goes to infinity, all the probability gets accumulated on that interval. And if you're back here at minus infinity, then your probability is 0, which is very physically making sense. Probability is like a mass per unit length or something, and it carries a weight, and that total weight is 1. And when you've accumulated all of it, you're sitting at 1. And then you can talk about the derivative of that being the density function, how the probability is actually spread over the line, and it's a non-negative function because probability can't be negative. It integrates to 1, and then the probability on an interval is some number, the probability of the event that it lies on that interval. And then if you go up to multiple random variables, you have joint CDFs and joint PDFs, which start to get pretty hairy, admittedly. And if you go take another type of class, you end up with random vectors where you have n dimensions, and the calculus turns into, n-dimensional integrations and things of that sort. We don't have that to deal with here, but we're going to talk about random processes in the last 10 minutes, get started on that. It is mind-boggling to think about a random process because it's actually an infinite dimensional random variable, and it's got an infinite number of dimensions. One of the things that will play up in the homework problems, though, in a very, very big way, is this fundamental theorem of expectation. And I'll point that out. But one of the first uses of it is to say, okay, let's find the variance of a random variable. Well, we can first find, when we work with this, and this is homework problem number 1 on set number 5, you've got some function of the random variable x, that's the boldface letter in this notation, that's your g of x. So you can expand that out into x squared minus 2x times mx, and then plus mx squared. So that simplifies down then into these two quantities, and that allows you to divide and conquer then and say that we find the mean square value and subtract from it the squared mean, and that is the standard deviation. So those types of calculations are pretty straightforward, and hopefully that's what you were thinking of, Miles, when you said you like statistics, because this is where the math is not that hard. You may have to integrate something, but in most cases you don't even have to do that. And then if we're going to have uncorrelated random variables, we can just have expected value of the product is the product of the expected values, and that is very nice and convenient too. And we'll be seeing that in our usage of it here. We have two fundamental PDFs that we'll rely upon. One is uniform PDF, and the other one is the Gaussian or normal. So the uniform is the one we use in quantization noise in our systems modeling, and it's just uniform on some interval, a to b, and then the height of the PDF is 1 over the width. So its area is equal to 1. Remember that? A PDF has area equal to 1, so the uniform one is nice and easy to work with. And the Gaussian one is not a central value to it. Well, there's a central value or mean value of the uniform too, and that's just a plus b over 2. That didn't come off very good, but maybe you have this committed to memory. I don't know. My memory says it's delta squared over 12, and delta is the width of the PDF for the uniform one. Whereas if it's a Gaussian or normal PDF, then the mean and the variance are already defined in the mathematical form as a term in the denominator. The exponent is sigma x squared, and then the shift factor in the numerator of the exponent is the mean shift, and it's then got these two parameters associated with it. And the variance controls the width of the PDF. And we can use functions like the Q function or the complementary error function to do calculations. We don't have any needs to do that calculation in this class, but I will refer to the tails of the Gaussian PDF for some of the calculations that go on later. So now, in closing, I'm just going to introduce the idea of the random process and then see where we'll go starting next week. So this is like a random variable on steroids of some sort or another. Rather than thinking of the underlying sample space, which is common to probability and then on to random variables, now we take the underlying sample space in each elementary outcome of the sample space, which in the case of rolling a die becomes like a number 1 through 6. In the case of the random process, rolling the die would create one of 6 different waveforms. Okay? And those waveforms could be anything. They could be a pseudo-random sequence of some sort. They could be, you know, a square wave, but different phases, let's say. So what we care about in the random sequence then is we have a signal, which is that sequence, which is what we have in DSP, and then we characterize what's going on over the so-called ensemble of sample functions that we have here, zeta 1 or chi 1, whichever group letter that is. And then we look at what happens down through one particular time instant, and we can say what is the mean and the variance at that time instant. And then if we shift it back and forth, it might change with time. And then we'll also be getting into statistics where we're going to sample at 2 different vertical sampling instances and then care about what is the correlation or covariance between those 2 vertical line points. And that is going to lead to then the autocorrelation function where we evaluate what happens as we lag at different time values. We'll have the so-called autocorrelation function. Now, it's hard. You're gonna have to, your brain's going to get stretched a little bit thinking about this, and you're going to do some problems. We're not going to dwell on this a lot in this class, but you're going to be introduced to these ideas. So I want you to be thinking about it, and your mind might start thinking random variables in practice too, an ensemble of events and such. So I'm going to stop here, but I'm going to point out one of the things on my website, though. There, I created an ensemble of discrete time, of 3 discrete sequences, and this was uniform noise stepping along in time with an equal distribution, but then it was charging up a filter. So behind this graphic is a filter that's discharged, like the capacitor's discharged, but it's a discrete time, you know, impulse response A to the n u of n, which we saw at the very beginning, and then the randomness of the waveform going through the filter produces a different sample function like that for each experiment. And if I was to look at the mean here versus the mean here, it would be different because it's going through a transient. We're going to avoid the transient scenario. We're going to assume it's in steady state, but it's kind of the nature of the way random processes work, though. And we'll have, it might be Gaussian, it might be uniform. We'll use both of them in types of calculations, and you'll be doing that in assignment 5. And then when I give you the take-home exam, you'll have some exercises where you get to run experiments in Python. See, Miles was telling me about, he likes, I think you said you like using Jupyter because you can run experiments on the computer and visualize things. So I'm going to have you do some of that in this assignment, 5, and then you'll do a little bit more of that stuff in the take-home. Because the take-home, you get to use a computer, and this is the perfect time to kind of close the loop on things, be able to write down the mathematical solution based on simple analysis, and then be able to run a simulation, get confirmation that it's working. What could be better? I mean, as an engineer, I like making things, but I like being able to know what it's going to do beforehand, and then I can test it and verify that that's true. And that's kind of one of my themes, is being able to verify all the way along. Math, simulation, test vectors from real systems. How does the system perform? Test vectors made up for simplicity. So the first problem, though, is random variables oriented. If you want to get started on that, but if you want to do coding for the project, like I said, from here on out, you're going to be having to split your time, and just, I know you may not enjoy it, but if you get tired of working on one problem, just go to the homework or something and flip back and forth. I mean, I've got stuff to do. I've got to work out a solution for the new problem. I've sketched it out. I've written all the code, but I haven't run the experiments yet. So I'm going to hopefully do that tonight, and then produce a notebook. That takes some time and practice, so pick one problem and just practice producing that, and that might, you'll learn what not to do, and that's what I want you to, that's what I'm kind of talking about here, is if you try one problem and it takes you a half an hour and you went down 5 dead ends, hopefully you'll say, I know exactly how I'm going to do it, and then as you do the rest of it, you'll just put that into practice. So don't try to do from top to bottom. You'll definitely.
When's the next homework due? 2 weeks?
2 weeks. It's in 2 weeks.
Cool. All right. Thank you.